said, okay, let's see if we can integrate. And let's see, so I have S is a cylinder here. And so I guess I could draw a little picture, right? And so, well, I have, let's see, x squared plus y squared is 9. I know that's a circle, so I can picture it on the xy plane going through, you know, this is 0, 3, 0, because that's usually the y-axis. And this is usually the x-axis, so that's 3, 0, 0, because my radius is 3. But also the cylinder has a height of 3. So up here you would have, you know, 0, 3, 3, right? So that's the surface itself. And so what we're going to do is my function f is just y, right? So that's kind of nice because I can just look at the y coordinate and I see, well, I'm going to get, you know, I guess the smallest my y coordinate would ever be would be down here. This point down here would be, if I point there, that would be 0, negative 3, 0, right? And up here, this would be 0, negative 3, 3, right? So I'm going to integrate y. And again, we're really only looking at the surface itself, not the whole cylinder, but the surface of the cylinder. So how do we parameterize the cylinder? I guess that's the question. And the book gives some really standard problems, right? Because coming up with a parameterization is not easy in general. But for a cylinder, well, you can let V be Z and let U be theta. And then basically what we're doing here is we're using cylindrical coordinates, which makes sense. If you see a sphere, you want to use spherical coordinates. But notice that with the sphere, your rho becomes kind of a constant. Here, I guess R becomes a constant, right, for a cylinder. So the constant is 3. This 3 right here, that's that I'm underlining here, that's this radius right here. 3. Okay. So we were trying to set this up. And so let's see, we want to do this. Okay, so I guess I had written down R because I was on my way to compute the normal vector, right? So how do we do the normal vector? We want the cross product. So let me show you exactly where we are. Let's get it here. Surface integrals. And again, this is where I wrote down n for my normal vector. Your book writes down t, I think, and they'll write tu and tv. So I just want to kind of show you, because when you're doing the homework, yeah, okay. Let's see what we have here. Right, they're going to do tu cross tv, but that's the same as what I wrote down for n, the normal vector. See, n is non-zero. So what we're going to do is we need the tangent vectors, okay? So here I go. Well, let's get R prime of u. Okay, so if I take RU of UV, okay, so I guess that would be negative 3 sine U, 3 cosine U, and then because u is the variable I'm talking about, I'm going to treat v as a constant, right? So the derivative of a constant is just 0. Okay. And rv of uv is equal to, well, here I'm treating these things as constants, so it's going to be 0, 0, and then 1, right? Okay. And so I guess my normal vector, n of uv, I get by doing the cross product of these, okay? So I need ru cross rv. And so that would equal, well, to write it down, I think it's helpful, again, if I put like an I here, a J here, and a K here, and then I just kind of look at this matrix and I say, okay, let's take the determinant of that matrix. What would it look like? Okay. So the I coordinate comes down to this determinant of that 2 by 2, so that's going to be 3 cosine u. That's the I coordinate. The J coordinate is going to be the opposite of if I had, again, eliminate the column J's in. So go, but it's the opposite, so it's going to be 3 sine u, right? And then the K coordinate, well, since you have a couple of zeros here and here, that's going to be 0, right? Is this okay? So now the other thing that I need for that integral, notice, is I need the length of n uv. And I think you can see that's 3, but let's work it out quickly. Because we would get, if you square this, you have 9 cosine squared u plus 9 sine squared u plus 0, right? Because it's x squared plus y squared plus z squared. And of course, cosine squared plus sine squared is 1. So I get the square root of 9, which is just 3. Right? Okay, so I think I'm ready. Here I go. Oh, I didn't put the limits of integration. I should do that. But I guess I know, because if u is theta, right? So then my u, theta is very constant here to be on the surface, right? Theta, I mean, we're going from 0 to 2 pi, let's say, for u. And v, right, v is going to be z, and it tells me that z is bound between 0 and 3. Right? So I guess, let's see if I can work this out now. All of a sudden, we turned this from a chapter 16 problem into a chapter 14 problem. Oh, wait, I can't write y. Ah, that's the issue. I have to change to u's and v's. So how do we express y, the y coordinate, in terms of u's and v's? Let's see. I guess if I'm on the cylinder, I'm satisfying this. Y squared is 9 minus x squared, right? So y is the square root of 9 minus x squared. So, okay, representing y is no harder than plus or minus than representing x.
Is it just 3 cosine u?
Or 3 sine u?
Or, yeah,
3 sine u? Because, yeah, I mean, in general, cylindrical coordinates, right? We know that x is r cosine theta and y is r sine theta. And so, yeah, in our example, r is 3 and theta is u. So let's say that this is 3 sine u. I like that. Let's throw that in for y. 3 sine u. And again, the length of the normal vector was 3. Okay, we're looking good. Let's see what happens. Integral from 0 to 3, integral from 0 to 2 pi. When we integrate u, let's see, we have 9, And the antiderivative of the, I guess, let me take another step. Okay, that's what we're integrating. So when I integrate sine, I get negative cosine, right? So I have negative 9 cosine of u. Weird. I'm already done. Why? Because when I plug in cosine of 2 pi, or if I plug in cosine of 0, those are the same, right?
No,
Right?
wouldn't we get negative 2? Oh, no, you're right.
No, 2 pi and 0,
Yeah.
I think I'm getting 1 minus 1 here, right? I'm getting 0. That happens a lot. That happened a lot in chapter 14 was, but what's different is usually there was like another piece that didn't have the trig function. So I happened to pick an innocent looking homework problem and the answer is 0. But I want to point something out. If you think about what we just did, what is a surface integral? It's like a line integral. We're adding up stuff. We're adding up stuff on the surface of the cylinder. What is the stuff we were adding up today? We were adding up all the y coordinates. Now think about it. What's the smallest y coordinate you could possibly get? I showed you it was negative 3, right? Right there. What's the largest y coordinate we could possibly get? I guess it'd be 3, right? And wouldn't you say there's all kinds of symmetry as you work your way around the cylinder? Like for every point, there's an antipodal point which has the opposite y coordinate. So this is very believable and it's correct. Okay? Yes?
What do you get
Yeah.
if you just do the, and what are you adding up if you don't do the y? If you're
So let's suppose that we integrated 1.
yeah, 1.
Let's do that.
Normal vector.
Let's do that. All right? So let's go back and try it again. So basically if we just, if instead of the y we had the 1, let's see what happens. That's a great question. Try again down here. I need a new color. Okay, so here we go. Double integral. We know it's integrate 0 to 3, integrate 0 to 2 pi. And I guess I still have that normal vector turned out to be 3, right? And this was du dv. Well, this is easy, right? So I get integral from 0 to 3, 3u from 0 to 2 pi dv. So I'm integrating 6 pi. 6 pi dv. 6 pi v, so you get 6 pi times 3, so you get 18 pi. What did we just compute?
Surface area?
That's the idea. Let's see if that's true. If you were back in geometry class, how would you compute the area of this cylinder? Well, what you'd probably do is you'd say, hey, I know what to do. If I have a cylinder, I take out a knife and I cut the cylinder, snip, 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 right on that dotted line. And that dotted line ends up here and here. And what I have is I have a rectangle. And I know how to find the area of a rectangle. The height is 3, which I point out was what that was right there, right? And the length is the circumference of the circle, which I remember learning was not pi r squared, pi times d, right? Or 2 pi r, some people say, right? So let's see, does that work? What's the diameter of this thing? Oh, that's kind of funny. It showed up there, didn't it? Yeah, 6 pi. So that's really, I think, instructive to see. A surface area integral is just the most basic form of a surface integral, but then you can have other kinds. Okay? So we're going to talk about Stokes' theorem. this is chapter 16, section 7. Awesome. And again, I guess this is generalization of the circulation form of Green's theorem. So again, you're going to want to know this for the exam, right? You're going to want to know what Green's theorem says for the exam. But what are we going to be doing for this homework? Okay, we're going to up it a dimension. That's really what's happening. So if we take a look, let's just see what it says. Well, first thing on the board that they're going to put is something we need to know. What's that? Okay, see that equation? Does that look familiar? Or is it all just gobbledygook right now? I don't know. It could be.
That looks like Green's theorem.
That's Green's theorem. Okay, that's Green's theorem. We have, how do I recognize it's Green's theorem? Well, we have on the left-hand side a line integral with the little circle meaning it's closed, right? So the circulation, right? The integral of f dr is equal to a double integral. And the double integral, what's r? R is the region inside. And when we learned Green's theorem, I don't know that we have this yet. We just wrote down gx minus fy. That's the curl, right? That's the two-dimensional version of the curl. Okay? So now we get to Stokes' theorem, and it's time to up it a dimension. So what does that mean? Take a look at the new. Oh yeah, this is really cool. I'm gonna make this nice and big so we can play with it a little bit. If I do this, you could see the whole applet. Okay, there it is. Right? So first of all, the theorem is written here. Yeah, let's write that down also. Okay, so the Stokes' theorem says, so we're going to write this. We're going to write, wait a minute, was that exactly the same? Yes, it was. Well, that's kind of cool. C f dot dr. That's exactly what we wrote down for Green's theorem. Equals. And when we had Green's theorem, what did we have on the right-hand side? A double integral. I'm still going to write that for Stokes' theorem. But the only difference is, instead of putting an A down here, I'm going to put an S here. S for Stokes? Is that a way to remember it? I don't know. S for what?
Surface.
This is a surface integral. So we study surface integrals so that we can relate them here. And it's just, whoa, wait a minute. No, I know what that is. This thing here in parentheses, right? In parentheses, I have grad cross F, but we studied that. What is that? What is that again? That's the curl. That's the curl. As opposed to what? What is grad dot F? Let's remember what that's called. Divergence, the divergence, right? So I think there were, you guys had in section 5, I think it's entitled Divergence and Curl. And there was that one section where they, hey, you know, do you have a dot product or do you have a cross product? That's really what's going on here, right? So for Stokes' theorem, we're going to have on this side the surface integral of the curl. And then we're going to write, check this out. So when you take a cross product, you get a vector, right? And then they say dot n. Why do they say dot n? Well, because that's, remember that's what we did in the last problem with the surface integral. You need to have the normal component, so that kind of makes sense. And then they're going to write ds. Fine. So this is our surface area. Okay? But the picture does what I can't. So this is really cool, I think, right? Select an integral. All right, I select this one. Show me what's going on here. So, well, let me select the other integral too, just to show you the difference, right? If I select this integral, oh, did I turn off the thing? I did. Okay, you get out of here. And you come back. Okay, after slight technical difficulty, we have it, right? So this is a surface, right? And so the curve that we're going to consider is the curve that is the boundary of the surface, right? If you were to integrate this thing, this is the curve you would project down onto the xy plane, let's say. Okay? So this is kind of cool. What is a surface integral? Remember how I said we're adding up lots of stuff all over the surface like we did for that cylinder problem? So check this out. I can move this somewhere else if it'll let me. I don't understand why it's not. Did before. There we go. It's slow, but it's chugging away. Trying to record. See? You can take this thing and drag it, in theory, and it'll put you somewhere else on the surface. Right? Here, let me move it just a little more, please. Okay. Well, whatever. And actually, it's computing that the curl right here dot normal component, right, is positive, it's saying. Fine. Where is the curl? Show it. Take it away. Yeah, this is just really slow right now, guys, and I apologize. It was not like this in my office, of course. Okay. Yeah, well, that's easier said than done. I guess what I should do is close MATLAB, because that takes a lot of memory. So, again, you can hit, you know, as I go around the boundary, right, f dot dr is positive for a while. But then once I get past here, now you'll notice that my angle changes, and so, you know, anyways, that's basically an illustration of the line integral. All right, let's go to an example. So let's try an example. Verify Stokes' theorem. Okay, so I need to give you an f, and I need to give you a little other information. So f is going to be, let's say, negative 3y, 3x, and z cubed. Okay. I also need to give you a surface, okay? So if S is the portion of the ellipsoid. Ellipsoid? Well, when I write the equation, you'll probably understand. 2x squared plus 2y squared plus z squared equals 1. Now, wait a minute. What if it said 2z squared? Then what shape would it be? Sphere. Bonus, what would be the radius of the sphere? Well, you'd want to divide all the 2's out, so you'd have a 1/2 on this side, right? And so the radius would be, right, 1 over root 2. You would take the square root of 1/2, right? Okay, so if we understand that, let's let S be the portion of the ellipsoid that is above z equals, 1 over root 2. Okay, so let's draw a picture of what's going on here. And so let's see. X squared and y squared come out farther than z squared. Z squared only goes up 1, right? And so I guess, at any particular place I have a circle, right? But up here at 1, I have, like if I threw in 0, 0, 1, that's a point on the ellipsoid. And if I threw in 0, 0, negative 1. And so I'm picturing kind of a sphere, but not quite. Right? So let me show you the difference. The sphere would look like this. The ellipsoid is, I had a sphere, but I squashed it, right? And that's why this only comes up to 1 and negative 1. You guys with me? Now, when I say S is the portion of the ellipsoid that's above this plane, so now I need a way of representing the plane. So where is 1 over square root of 2? Well, that's that's higher than 1/2, right? Because the square root of 2 is smaller than 2. If the square root of 2 is smaller than 2, I'm dividing by something. So let's see, here's 1/2. Here's a little bigger than 1/2. So if I could imagine a plane containing that point, this is the plane z equals 1 over the square root of 2. Now wait a minute, what would the intersection look like of this? Well, it would be a circle, right? It would be a circle where, I don't know, maybe here? Are you with me? We're trying, Paul. Your drawing stinks. Okay, well, I'm trying. Something like that. Let's sneak this picture in real quick. Ha-ha! Ha-ha! Much better than mine. Okay, now. But here's our example. Okay? I think this is worth doing. The visualization aspect of this, forcing you to think 3D a little bit, forcing you to think about where things are. All right, time to do the calculations. So let's see. We can think of this surface, right? So S is the graph of the function z equals, well, I could solve for z, right? I'll just do 1 minus 2x squared minus 2y squared, and I'll take the square root. I know I'm normally supposed to do plus or minus, but this is clearly plus because I'm above the xy plane, right? Okay. And so that's my function. And what else do I need? I need, well, I need to think about the gradient cross f, because that's going to be involved, right? I mean, Stokes' theorem says we have that. So I'll need to do gradient cross f, and I'll also need a normal vector. So let's see. I wrote this as z, but I guess I could also write it as r of uv if I want to use the current notation we've been using, and just think of it as 1 minus 2u squared minus 2v squared. Is that okay?
That's not a vector. Well, I mean, I guess it's not in the
It's a
policy thing.
it's a parameterization of the surface.
Okay.
I mean, it's a waste of time, you could argue, because Paul, all you did was turn the letter X into the letter U and the letter Y and the letter V. But the reason I'm doing it is I want to show you that it really is the same thing, right? This is a surface integral that we're going to compute. I don't care which way we handle that. I do want to compute the curl. So let's see, how do I do this? Well, again, for a cross product, I usually do I, J, K. Oh, but what's the gradient vector? What do we write? Partial derivative, right? Because it's the vector of partial derivatives. It's this operator. And then for f, we were given that. That was negative 3y, it was 3x, and it was z cubed. All right, so let's see what that ends up equaling. The curl is, okay, when I take I, I'm taking the partial of y of z cubed and the partial of z of 3x. This is a nice problem. When I do j, partial of x of z cubed, partial of z, and when I do k, 3, minus negative 3. So this is, well, how do you want to write it? 0, 0, 6. Is that okay? That's one way to write it. Okay. Dot n, yeah, we need the normal vector, right? So again, what would happen if I did things like RU? Well, I would get, let's see, 1/2, because that's the bing from the 1/2 coming down. And then I would get stuff to the negative 1/2 times, when I get negative 4u, does that look right to you guys? So RU is going to be, I guess, negative 2u over the square root of 1 minus 2u squared minus 2v squared. Is that okay? And if you believe that, you'll probably believe that RV is going to be negative 2v over square root of 1 minus 2u squared minus 2v squared without me showing any work. Okay. So now normal vector. I guess RU cross RV of course, maybe I should go back to X's and Y's just to be comparable. Back to our problem, back to our program. Yes, I did hear you, Sullivan, when you said, wait a minute, that's not a vector the way you wrote it. I wrote R of UV equals square root, and I'm getting myself in trouble. So let me continue on the next page. These pages are precious now, but let's take this stuff that we calculated and keep moving. Here. I wrote down R instead of using the u's and v's, let's stick with the x's and y's. Because like I said, why change letters? But I really do want to write it as a vector. And I can do that if I say, well, we have x, that's the x coordinate. We have y, that's the y coordinate. And we have z, but I already solved for z. That was this square root of 1 minus 2x squared minus 2y squared. So there's r. Okay? Then if I want the normal vector, I'll need to compute rx and ry. Well, I already did that. I remember I got rx was negative 2y over the square root of 1 minus 2x squared minus 2y squared. But when I say that that's rx, that's not quite right. Rx is a vector, right? That's what I did wrong. So that's the z coordinate, because that's the partial derivative of the z coordinate, right? What would be the x coordinate? And the y coordinate would be 0, right? So that's the real Rx. And now when I do Ry, well, same thing. I get 0, 1, and I already worked out for you guys that this is negative 2x over the square root of 1 minus 2x squared minus 2y squared. So there's Rx and Ry. So now I'm ready for the normal vector. N equals, well, what does it equal? Again, if I want the normal vector, the thing to do is to put ij and k up above. Question?
Yes.
Go ahead, Alex.
Why is Rx negative 2y and not negative 2x?
You're right. It's negative 2x. And this was negative 2y. That is what we computed. You're right. Thank you. Okay. So saved by Alex, here we go. N is equal to, the first coordinate, I, is the determinant of this matrix. And notice I have 1 times a negative, but I'm subtracting it. So the first coordinate, I guess, would be 2x over the square root thing. For the second coordinate, I chop out the middle row and I see 1 times negative, 0 times something else. And so I get, but because it's j, I have to do negative, so I get 2y over the square root thing. I'm just sick of writing 1 minus 2x squared minus 2y squared. Plus, I can see what's going to happen. What do you get for the z coordinate? Well, you just get 1, right? And remember what we're about to do. We're about to dot this, right? We're going to remember we were interested in the surface integral, right? Of what did we have? We had the curl dot the normal vector, right? ds. That's what it was from the previous page. Okay? Well, the curl we worked out was what? 006, right? So that's 006. So I dot that with this, and I find out, oh, this is a nice problem. I just have to integrate 6 ds. But again, here's where the parameterization comes in, right? So let's see. Well, one thing we could do is we could say it's 6 times the surface area. right? So I think it's worth it to do it though. Let's see. So how would we do this problem? We want to use our parameterization of the surface like this. This is going to take more time than I expected. Okay. For your reference when you're trying these problems, okay? Because as I said, now we've just reduced it to defining a surface integral, right? But the trick a lot of times is the parameterization. And this table is going to come in handy if you're trying these Stokes theorem problems. You go back a section, table 16.2 on page 1135, you might want to make a note of. Right? What do they have? Well, kind of some of your basic surfaces. Cylinder, cone, sphere, paraboloid, right? They list the normal vectors n, which is kind of nice. And then they also give you a parametric description also. So we did something kind of like the paraboloid, but of course ours is different because we have our z is the one that's interesting, I guess. So that comes in handy for a lot of the problems, but not ours because we don't have an ellipsoid sitting here. Okay, but I'm just pointing that out that may be helpful for you guys when you're doing your problems. Okay. I think there's a mistake here. Okay. I mean, this is okay, what I wrote here. I mean, yeah, that's what we're computing. But when I make this 6, I don't have to write it as a surface integral any longer. And that's kind of, because let's go back to line integrals, what you guys are working on more now, okay? When you have this kind of situation, we write down C, and we write down, oh, what kind of thing? I don't know. You'll have some function in here, right? And then what do you guys usually write here for a line integral? Well, for example, sometimes we write f dot n, right? dr. You guys have written things like this, right? But when we compute line integrals, what we do is we want to write dt here, right? We change it to a parameter. And so then you guys will write things like, 0 and 2 pi or something like that, right? And you'll have some function of t. This is what you guys have been doing, yes? So when I want to compute that, the whole trick, right, is we need to use a parameterization. When I use a parameterization, think of the slider that we had in the other example, which goes from 0 to 2 pi, right? I'm just, instead of dividing the curve up into pieces, I'm just dividing, when I write dt, I'm talking about t ranging from 0 to 2 pi. I don't know if this is making sense, guys. I'm trying. But if you understand that, then what I'm going to do over here is I'm going to say I need to use my parameterization of the surface S. Well, what was my parameterization of the surface? It's up above, right? R of xy is this, right? That's my parameterization of the surface. But what I didn't write down is, where do x and y live? And the answer is within a circle. Let me show you. It's on the previous page in my wonderful drawing. Here. That green circle is the boundary of the surface that I'm interested in up here, right? How do I parameterize that surface? Well, I did it in terms of x and y, but the x's and y's live in a circle down on the plane z equals 0, right? They all live here. What is that circle? Let's draw that. Let's call that region R, by the way. So it's a circle, and the circle is the intersection, right? This was the intersection of z equals 1 over the square root of 2 with S, the surface, right? So if I want to ask, well, okay, what does that look like? I take my parameterization, there it is, and I set z equal to 1 over the square root of 2. So I have the square root thing. 1 minus 2x squared minus 2y squared is equal to 1 over the square root of 2. If I square both sides, I get 1 minus 2x squared minus 2y squared is 1/2. Or I get 2x squared plus 2y squared equals 1/2, right? Or I get x squared plus y squared equals 1/4. And this is a circle with radius 1/2. And so the picture of where do x and y live? They live in here where this is the point 1/2 comma 0, and this is the point 0 comma, I guess it'd be negative 1/2, right? So they live in here. And so this region I'm going to call R. And so back to my analogy. When you do line integrals, you write a parameterization. When you do a surface integral, we're going to use a parameterization. Okay, so now I'm here. We write it as a double integral of 6, and I guess I could do dx dy, right? But maybe it's even easier to do this. Let's do a double integral and do 6 r dr d theta, right? Here I am reviewing yet another section of your book. It's funny how this sums up everything in 2 sections. Stokes' theorem and the divergence theorem. All right, what should my thetas be? Let's go from 0 to 2 pi, right? What should my r's be? Let's see, is that true? Yep, 0 to 1/2. And can we integrate this? I hope so. Let's see. When we integrate dr, we get r squared over 2, so now we have 3r squared. And we're going from 0 to 1/2. And then we still have to integrate d theta. So we get, that would be 3/4 integral 0 to 2 pi d theta. And so I'm getting 3 pi over 2. How's that look? Looks pretty. Okay. Did we verify Stokes' theorem? No, we did half of it. Because, wow, what we showed so far was
One side works.
this side gives us a nice answer of 3 pi over 2. Now, let's show that we can compute the same thing as a line integral. So how do I do that? Well, I need a parameterization of this green circle. What do you think, Matthew? That laugh just looked funny to me. I don't know.
No, just noticing that we gone through a page and a half of notes just on one side of the problem.
I'm on my last page of the notebook. This is our second notebook this semester. It's wonderful. All right, so how are we going to do this? Well, let's see. It is a closed curve, f dot dr. How do we compute that? So, let's see. F, do we have that? We do, right?
Yes.
We have
3x, 2y,
negative 3y, 3x, and
z cubed.
z cubed. Or was it z to the fourth?
I have z cubed.
Okay. I have z cubed. But that's really funny. Okay. Oh, it's been one of those days. So I'm going after this circle. This, let me get a better color. This circle right in here is what I'm going to call my curve C, right? And the point is that if we can compute the line integral around that curve, that should be the same as the surface integral over the surface we just did. This should be shorter. But we need a parameterization of that curve. Now, I guess what do we know? We know z is 1 over the square root of 2, right? Okay. So if I want to, parameterize it, I guess I know that the z is 1 over the square root of 2, so that's kind of nice. Now, what about x and y? We know how far out they go. We just did that, right? Oh,
1/4 cosine theta, or cosine theta.
why would it be 1/4? Yeah, because,
That's the radius.
well, wasn't a radius 1/2?
Yeah.
I think we had x squared plus y squared is a quarter, and the square root of a quarter is a half, right? So this is basically radius 1/2, right? And so, yeah, can we write 1/2 cosine t and 1/2 sine t? And now we're in the world of line integrals where we have a parameterization of the curve. So again, I've been using r. We'll call this r of t. That seems to work. Okay. So let's see. F dot dr would be integral, and I guess, let's see, we can do what was the original? Oh, I see. So f was this, negative 3y, 3x, and we said z cubed, right? dot,
These will go away.
because we're dotting this with what? dr. So dr is dx, dy, dz, right? Let me think for a moment. Again, since r of t was 1/2 cosine t, 1/2 sine t, and 1 over the square root of 2, then what goes there, my dr, is going to be, let's see, dr, right, would be negative 1/2 sine t, 1/2 cosine t, and 0, right? So that's what I throw there. And now we're turning this into a dt integral. Negative 1/2 sine of t, 1/2 cosine t, and 0. Oh, and what should be the limits of integration?
This works really well.
0 to 2 pi, right?
I like this one better.
So we get, yeah, integral from 0 to 2 pi of this dot product. So let's see. Oh, it doesn't quite work yet because I need to, well, what do I need to write instead of y if I want to write a dt integral? I guess,
1/2 sine
yeah, change that to 1/2 sine t, right? So the 1/2 sine t gets thrown in for that y, and similarly, the 1/2 cosine t gets thrown in for that x, and I don't care what you throw in for z because we're dotting it with 0. Okay, then we really have a dt integral. But this is basically how it works. So now we have integral 0 to 2 pi of what? Let's see. So we have negative 3 halves times negative 1/2. That's positive 3/4 sine squared t plus, and then here I have 3/2 cosine times 1/2 cosine is 3/4 cosine squared t. Yep. This is really nice. Plus 0 dt. So we're going to integrate from 0 to 2 pi, 3/4 dt. So we get 3/4 of 2 pi, which once again is 3/2 pi. We verified Stokes' theorem. Hey guys, I don't think I'm really the right person to teach you the intricacies of Stokes' theorem. Not at the point I'm at now. But what I am able to do is help you work through the problems and verify things like this, and you'll notice that along the way we've practiced a heck of a lot of Calc 3 in one problem. That's my reason for wanting you to do some of these, okay? You are getting into these calculations that are done in the physics classroom, that are done in the engineering classrooms, that you will do later in college. But not only that, you're reviewing all the techniques that we've taught you in Calc 3. It really is kind of a nice capstone section, this Stokes' theorem. And you'll see next time the divergence theorem is as well, okay? So I'll probably do 1 or 2 of those, and that's going to be about it. Other than that, I'm going to help you guys review for this final. That's the best thing I think I can do. Okay.